a single person do an Eratosthenes experiment all on their own without having to travel over the entire world. This is the 21st century. We have technology, we have astronomy tools, and we have data that anyone can double check, verify, or falsify. So back in March, 9 real human beings did a real Eratosthenes experiment with sticks and shadows. No NASA, no CGI, no cartoons, just sticks, shadows, sunlight, and measurements. And the results were pretty damn good. Using the 2 most accurate measurements right here, we calculated Earth's circumference within 81 miles of the actual size. And since then, I've been testing some things. I took my updated 3D printed apparatus, measured the angle to the sun at solar noon here in Phoenix, and compared my results to dateandtime.com. Now, date and time gives you solar noon and the sun's altitude angle any day you choose for pretty much anywhere on the entire world. There is a mildly annoying part with date and time where it rounds the sun's angle here, you can see the altitude, to the nearest whole number. With my device, we calculate within 2 decimal points. But after checking about 5 different times over the last 3 months, my measurements were consistently very close to timeanddate.com. So for Phoenix, we know that this data is accurate, and that gives us pretty solid reason to treat their global data as reliable. And if someone thinks this data is wrong, perfect. Go outside and verify or falsify the information yourself. That's the whole point of science. For the test we're doing, I used March 21st, the same time the group of 9 of us did this before, right around the equinox. And I picked locations stretching from near the equator all the way up to northern Alaska. So we have Panama City, Panama, Mexico City, Mexico, Miami, Florida, Phoenix, Arizona, Seattle, Washington, Anchorage, Alaska, and this town way in the north that I'm gonna butcher the name of, that's also in Alaska. And we got all their data. So here's the one in Alaska. Ute something of it. I can't do it, but we've got an angle of 19 degrees. In Anchorage, we've got an angle of 29 degrees. In Seattle, an angle of 43 degrees. In sunny Phoenix, Arizona, 57 degrees. Miami, Florida, 65 degrees. Mexico City, Mexico, 71 degrees. And Panama City, Panama. You have to look up at 81 degrees to see the sun. Now I plotted them all in Desmos. So first we've got the globe here. It has a radius of 3969 miles. Then we have little dots where all the cities are. And we've got lines shooting off at the correct angle towards the sun. And look what happens. All these lines come off the globe almost parallel. This is exactly what we'd expect with the sun far away. And if we extend those lines out 93 million miles, the lines behave almost exactly how the globe geometry predicts. Now they aren't perfect, and the reason is simple. When we use the sun's angle with these measurements rounded to the nearest single degree, it's not perfectly accurate over extremely long distances. So if we change Miami here, that's this green line, it'll just make it easier to see the difference. You can see where it's at, and if we change this by just 1/10 of a degree, it's dropped 1.5 of these squares. So let's go down to where it would round up to 65 even. You can see that's moved where it's just touching the top of the sun almost. So this is where rounding to the nearest whole number makes us slightly off alignment, but it's almost perfect. So the issue isn't the globe model. The issue is we're using rounded numbers from public data. If I wanted more precise numbers, I could use something like Stellarium, NOAA, or other solar calculation programs that give us the sun's angle to decimal places. But I wanted to start with something simple that everybody can use, and dateandtime.com is a pretty simple tool. Now let's plot the same on flat Earth. So near the equator, Panama City right here is looking up at 81 degrees. And as we move farther north, the sun gets lower and lower in the sky. So that sounds perfectly normal, but the geometry starts to fall apart really fast. On the flat Earth setup, the orange line is the sun's ground position over the equator. And when we use the observer's angle, each location gives us a different height for the sun. You can see here that if we're in Panama, the sun's elevation is almost 3,900 miles. Then Mexico City, about 3,800. And it goes down and down. And if we go all the way to northern Alaska, according to flat Earth, the sun is sitting about 1,700 miles above the surface of Earth. So, according to flat Earth geometry, the sun physically changes elevation by over 2,200 miles, depending on where the observer stands. That's not a small error. That's definitely not how perspective works. That is not, you just don't understand flat Earth. That is flat Earth failing with very basic geometry. And on the globe, the sun's angle produces nearly parallel lines pointing towards a very distant sun. On flat Earth, the exact same data gives you a sun that magically changes height by thousands of miles. But as we all know, the point of the Eratosthenes experiment over 2,000 years ago was not just proving Earth was curved, it was calculating the circumference of Earth. So let's try that. What I did was scanned around Google Maps for a long time to find a very straight road that has a long distance. And the best I found was Denton, Texas, up to Salina, Kansas, following the I-35. It's nowhere near as straight as I would like it to be. It does zig and zag a little bit, but it's relatively close to straight, and in reality, any person could hop in their car, drive this route, and verify that distance of 407 miles. For this one, I used the NOAA calculator because we get the angle of the sun to 2 decimal points. All you have to do is plug in your latitude, longitude, the date, and the time, and we get the angle. So we plugged all that in. We have the latitude of Salina, the latitude of Denton, which we did use. I did use dateandtime.com to get those initially. Then we have the angles to the sun, according to NOAA, the driving distance of 407 miles. And just to do quick math here, I did do the division, and we know that Earth's circumference is about 69.1 miles per degree. We got 72.3. That error is because, as you can see, this isn't exactly a straight line to drive. So it does give us some extra miles. But using that data, even with this imperfect setup, and we do the math, we got that Earth's circumference is 26,071.2 miles. Now we know that the actual circumference, this is the polar circumference, so over the poles, is 24,860 miles. This is what we're told. I haven't gone out and measured it, but it's given to us. By doing this, we have a difference of 1,200 miles, or 4.87% error. And honestly, for one person using internet data and a wobbly highway route, this is pretty damn good. Could it be better? Absolutely. If there's anybody that knows of a straighter route that's 300 to 400 miles, almost vertical, north to south, south to north, let me know in the comments, because I'd love to test this again with a better route. But even with imperfect tests, the results are still ballpark of real Earth. Not 10,000 miles, not 100,000 miles, not flat, not we don't know, like flat earthers like to just spout because they think science is scary. We got a globe with a circumference very close to what we already know. So as one person sitting at home using public data that anybody can check, you can do an Eratosthenes experiment test all on your own. Check sun angles out in your backyard, compare cities, test geometry, and you can estimate the circumference of Earth. But once again, when we test the globe and we test flat Earth, one of them keeps working and the other one completely falls apart. At some point, you have to stop asking why globe evidence keeps matching reality and start asking why flat Earth only works until you do the math. So thank you for coming to my TED Talk on how you, all by yourself, can use shadows, sun angles, and publicly available data to estimate the size of Earth and show that the sun is not local. No rockets, no NASA, no faith required, just geometry and a few minutes of your time.